Hey everyone, I'm making this quick video because this is a question that I've got asked a couple times by several different students, and that question is, how can I tell whether or not a molecule forms a particular type of intermolecular force, or how do I know if a molecule has a particular type of dipole? So the type of intermolecular force that's formed depends on the identity of the charges that are on a molecule. And so I'm going to walk you through how to find or not find different types of charges. So we're going to start with the one that's the easiest to identify, or not the easiest to identify, but the one that has an explicit charge on the molecule. And so those are molecules that have ionic charges on them. Now, in this class, most of the ionic charges we've seen have been with metal ions or individual ions, such as like Na+, Co-. But we've also seen these with polyatomic ions such as sulfate. Alrighty. So an example though that I'm going to show you here is this is an acetate ion right over here. Alrighty, and so the way that I would know that this molecule could form ion-dipole interactions is that it has an ionic charge. Whenever a molecule has an ionic charge, that charge will be explicitly written as a -1 or a +1 next to that atom. So if it has a non-zero, if you have a molecule that has an atom with a non-zero formal charge, it has an ionic charge and an organic molecule, that molecule can ion dipole with itself. Okay, so then comes the next one down, and this is where things get a little tricky because ion dipole arises from an explicit charge on an ion, but the D in dipole comes from implied or implicit charges. Okay, so those are charges that are on the molecule, but they're implied because they're partial. And the secret to unlocking and identifying where dipoles lie comes from identifying whether or not a bond is polar. Okay, so for instance, if we go back to acetate again, the way that if I give you a problem where I ask you to look at a molecule and to identify the type of intermolecular forces, you want to make a map of the charges in a molecule. So you start by identifying any ionic charges, and then you try to find dipoles. The way you can go about hunting for dipoles is determining whether or not bonds in a molecule are polar or nonpolar. And we do that by consulting our electronegativity table. So let's start here with acetate, alrighty? So a carbon-carbon bond right away, that's going to be nonpolar. So we can assume electrons are evenly shared, so we're not going to touch it. Carbon and hydrogen, electrons, I think it has an electronegativity difference of 0.4, so that's less than our cutoff for a polar covalent bond. So we will also assume that carbon-hydrogen bonds are nonpolar. However, with carbon and oxygen, a carbon and oxygen bond is polar. Oxygen is more electronegative than carbon, so that oxygen is going to pull the electron density towards itself away from that carbon, and we draw that with a dipole arrow. We can also represent that with a partial negative on the oxygen and a partial positive on the carbon. Now, this molecule can ion dipole with itself because you can have the positive or the negative ionic charge on oxygen on one molecule interacting with the partial positive charge on the carbon of another molecule. Alrighty, so another version of itself that's floating around in solution. Okay, so what I want you to do now is I want you to go through all of these molecules. I want you to identify all the polar bonds and then draw in all the dipole arrows that indicate which direction the electrons are being pulled. If the bond is nonpolar, then leave it alone. Okay, pause the video, and then when you press start, I will have drawn in all the dipoles and the partial charges. Okay, all right, so again, carbon-carbon bonds, same atom, nonpolar. Carbon-hydrogen bonds, electronegativity difference is smaller, that we ignore it. But all of these bonds that are carbon-oxygen or oxygen-hydrogen, and these molecules are polar. So with ethanol over here on the left, we have a partial positive on a carbon and a hydrogen, and then a partial negative on our oxygen. And then over here, we have a partial positive on our carbon, and then a partial negative on that oxygen. Okay, so this is the process. So dipoles are implied because we have to go in and identify and unpack and then distribute the electrons across nonpolar covalent bonds. So then the question becomes, how do I know if a molecule participates in dipole-dipole or hydrogen bonding? So hydrogen bonding is a special type of dipole-dipole that happens when the partial positive is on a hydrogen that's attached to an electronegative atom, specifically oxygen, nitrogen, or fluorine. So for instance, this hydrogen over here can't participate in a hydrogen bond because it's attached to a carbon. This one also can't participate in a hydrogen bond, even though it's attached to a carbon that's attached to an oxygen. That's not enough. However, if we look over here at this hydrogen that's attached to the oxygen on ethanol, this hydrogen can, in fact, undergo hydrogen bonding. And so the way we would draw that is if we were to draw in another molecule of ethanol, that partial positive on the hydrogen would be attracted to the partial negative on an oxygen, another ethanol molecule, and we can draw that attraction by a dashed line. Okay, so I told you that over here on this molecule, we can't hydrogen bond because we have an oxygen, so there's a polar bond, there's a charge separation, there's dipoles, partial negative on the oxygen, a partial positive on the carbon, but we can't hydrogen bond with that hydrogen. So what's left? This is where dipole-dipole comes in, alrighty? All right, so if we take another version of that molecule, the partial negative on the oxygen will be attracted to the partial positive on a carbon of another molecule. So this would be a dipole, and then this would be an ion dipole. Okay, finally, that brings us to our last molecule, which over here would be ethane. Alrighty, so with ethane, if we look at these, we didn't put on any dipoles there because there aren't any bonds that are polar, at least bonds that are polar enough for us to bother with drawing dipoles. So it doesn't ion dipole, it doesn't dipole-dipole, it doesn't hydrogen bond. So that leaves one type of, it only has temporary dipoles there, alrighty? So temporary dipoles that arise from the electron clubs moving around the carbon and hydrogen atoms. So the best we can see here is London dispersion forces. And again, every molecule has London dispersion forces because every atom, whether it's a hydrogen or carbon, or whether it's this oxygen on ethanol or this oxygen over here, they all have temporary dipoles. It's just with these other molecules, the hydrogen bonding, the dipole-dipole, and the ion dipole overwhelm and become more important than the London dispersion forces. Alrighty, I hope this video was helpful.